My name is Prince Araf and I am now going to tell about electrodynamics. Electrodynamics is basically the branch of physics, classical physics, which deals with the study of electric field, magnetic field and their interactions with charges and current. Electrodynamics was first invented by Hans Christian Ørsted while discovering the magnetic effect of electric current, and was finally unified and to make electrodynamics by James Clerk Maxwell, a great theoretical physicist from United Kingdom in the year 1865. And what we are going to discuss now is Maxwell field equations. What are Maxwell field equations? These are the most fundamental basic equations of electricity and magnetism which unify together through his own physical significance. So what are the mathematical requirements of the Maxwell field equations? Here we can see d a vector. d a vector means divergence of a vector. A vector is a vector field, and mathematical requirement means that what we need in the Maxwell equations from mathematics to know about. So now divergence of a vector, that is a vector field, is denoted by del vector dot a vector, okay, equals, its meaning is that the partial derivative of a vector, that means the partial derivative of a vector with respect to the partial derivative of x. Here is the meaning that the partial derivative of a vector or at the component of x with respect to the derivative of x. So now the partial derivative, the x partial derivative, we can simply read it is the x partial derivative of x component of a, okay, plus the y partial derivative of y component of a, plus the z partial derivative of z component of a. Now what is partial derivative? Partial derivative is very simple. The function is variable and we have to differentiate a particular function with respect to which was given by the independent function, okay. So that is partial differentiation. It means that d by dx we have know about this, okay. But what is partial derivative? So partial derivative is the function when is given very variable function xy, that means f of xy, and with respect to what, let's say x. So then we have to take y constant and differentiate fx. So that is the scenario of partial differentiation. Partial differentiation, that means, is same as the simple differentiation, but it is for variable um, uh, functions, okay. Now what is the meaning of the divergence of a vector? The physical meaning of divergence of a vector is the flux of a vector in a closed surface, okay. The flux of a vector in a closed, any closed arbitrary closed surface. So now let's take example, the closed surface. Now there is a vector flowing here, okay, and now we have take that surface with the angle of theta, and that is a closed surface. So the number of total field lines of a vector that is touching this closed surface, which is here is a closed surface at the angle of theta. So that is the physical meaning of divergence of A. That is the divergence of A. Okay, so that is the physical meaning of divergence of A. That means we will going to use it in the Gauss's law of electric field, the flux, electric flux, so then we use that flux of a vector in closed surface. So this is given, that the flux, electric flux, the magnetic flux. So this is the meaning. Now what is the curl of a vector? The main thing, we have to understand this mathematically. The mathematical understanding of the a vector and the divergence and the curl of a vector is given there, and the physical understanding, which is the application for understanding for application, is given here. Now the mathematical understanding is that curl of a vector is denoted by del vector cross a vector. Here is dot, here is cross. Okay, now uh, it is given by the mathematical expression of determinant of I cap, j cap, k cap, partial derivative, x partial derivative, y partial derivative, z partial derivative, ax, az, the determinant of this. Okay, so that is the mathematical expression for curl. And you know what is determinant? We have studied that it is the how can we calculate it? By this method, for taking I. So let's common I. What we have? D by d, y partial derivative, z partial derivative, y a x of y component, and a of y component, and a of z component. Okay, now taking common of j, so what we have? X partial derivative, z partial derivative, a of x component, a of z component. Taking common of k, what we have? X partial derivative, y partial derivative, a of x, a of y. Now what we have to do with this? We have to calculate the scenario now, which I am going to write, that taking the plus minus plus symbols and I j k cap. Okay, now to write I cap, we have to determinant of that d by dy, d by dz, ay, az. Okay, and here is the minus symbol, here is the plus symbol, so there is the plus symbol, which is not given here because we can, now minus symbol is given there, and taking which. Okay, now d by dx, d by d z, and ax, az, and determinant closed. There is j cap. Okay, j cap plus what? Plus the determinant of d by dx, d by dy, ax, ay, determinant closed, and here is k cap. Okay, so this is the determinant. And how can we calculate this? We calculate by this d by dy of a z minus d by dz of ay. Similarly with this, and we can calculate at last. So that is the curl, mathematical expression for curl of a vector. And the physical significance of curl of a vector, physical meaning, that is the circulation of a vector around a closed loop. The circulation of a vector field around a closed loop. That means what? Just like you take Faraday's law. Faraday's law of electromagnetic induction tells that the change in magnetic field, the change in magnetic field lines through a particular area nearby a coil induces a EMF in the coil. So the circulation of that EMF here is a vector. A vector means the vector field. Vector field here is EMF. Okay, and the magnet which is moving, through which the flux is changing, and there is the induced EMF. So that here induces, and there is this, that is the circulation, of EMF. So the circulation of EMF is denoting by this. Okay, so that is the meaning of curl of a vector, the circulation of a vector around a closed loop, this is the closed loop. So the circulation of a vector around a closed loop is given that in mathematical physics is the curl of a vector. Now this was the mathematical requirements for Maxwell field equations to understand. So Maxwell's field equations are, now I'm going to write. First is Gauss's law of electrostatics. We are completing whole electrodynamics in this single lecture. Gauss's law of electrostatics, what is that? This is the divergence of electric field is charge density divided by epsilon naught, that is the magnetic constant for free space, sorry, electric constant for free space. So that is the Gauss's law of electrostatics. Okay, this is the first Maxwell field equation. It is for electric field, steady electric field, that is electrostatics. Second is Gauss's law of magnetostatics. And it is given by the divergence of magnetic field is always zero. Okay, so that is the second Maxwell's equation. Okay, divergence of magnetic field is always zero. It is that the flux of magnetic field in a closed surface is always zero. That means there is no generation or absorption of magnetic field in the whole universe, the whole system. So that is the meaning of this equation, physical meaning. Now it also tells that the magnet cannot be separated, the north and south pole, the north pole and south pole of magnet cannot be separated to each other. And if it can be separate, so the Maxwell's equations get wrong, and there will be the revolutionized step throughout the history of physics. Revolution, this will be the scientific revolution. Now what is electrostatics? The physical meaning of electrostatics is that the divergence of electric field, that means the flux of electric field is directly dependent in throughout the closed surface, is directly dependent the presence of charge density inside that closed surface. So this is telling this. Now third is Faraday's law. Faraday's law of electromagnetic induction. Electromagnetic induction. Okay. Faraday was not mathematically mature. That means he was not understanding higher mathematics. So that's why he cannot derive these equations. These equations was derived then by James Maxwell. Now, this is given by the curl. These are the divergence, but here is the curl of what? Curl of electric field equals negative time derivative of magnetic field. Okay, that is Faraday's law of electromagnetic induction. The physical meaning of this equation, this mathematical expression, is that the circulation of electric field, I was telling this law here, that is circulation of electric field. The circulation of electric field is given by the negative time derivative. That means the negative motion. The negative motion means the Lenge's law here. Negative the sign, Lenge's law. The motion of magnetic field. Magnetic field moves and it produces a circulation of electric field around a closed loop. Here is the main point, around a closed loop. Okay, so this is the main. All we have to do is to consider these mathematical requirements in our mind and use this to apply in Gauss's law of electrostatics, magnetostatics, Faraday's law, and the next law. That means the Maxwell's equations. Then we can understand the physical meaning of these equations. Now, these are very simple equations to understand. So that's why I'm going to tell you. This is the Maxwell's law of electromagnetic induction. On the basis of this, we can invent, we can make a motor, electric generator, many things. The whole global scenario is revolutionized by the application of this law. So now, fourth is modified Maxwell's. Here is the Maxwell's own contribution. Maxwell's own contribution is that Maxwell's modified what? Ampere's law. Maxwell's modified Ampere's law. Ampere was the Newton of electrodynamics, as told by James Clerk Maxwell. He was the Newton of electrodynamics. But what he mistaked, that the curl of magnetic field equals only mu naught, that is the magnetic permeability in free space, which is also called magnetic constant, times J vector. What is J vector? Current density. So that was Ampere's law, but Maxwell modified it, and to add that mu naught epsilon naught, magnetic constant, electric constant. Epsilon naught means the electric permeability in free space. Okay, now time derivative of electric field. Now, time derivative of electric field. He added this term. And this was Maxwell's own contribution to the field equations of electrodynamics. So here is the modified Ampere's law. Tells what? The meaning of this equation is somewhat a level up by as compared to these equations. What is the physical meaning? Now, the curl of magnetic field, the circulation of magnetic field around a closed loop. A closed loop, around a closed loop, the circulation of magnetic field is given by the uh, so we have to forget constants. We have to forget constants to understand this. Now, current density. The current density, the total amount of current divided by the what? Area. This is the current density. So, it is given by the current density. Now, we have to understand this. How can I understand? We understand by drawing the diagram. Here is a current carrying wire, and here is the magnetic field. Magnetic field. Okay, magnetic field. Now, these magnetic fields is given by the current density, that how dense these currents flows uh, decide the circulation of magnetic field. Okay, this term completed, understood. Now, um, we forgot this equation, this constants, because we have to understand the variables. Now, the negative I'm telling, sorry, the time derivative of electric field, the time derivative of electric field decides the circulation of magnetic field. Okay, this was Maxwell's own term, because for displacement of current, so Ampere only write this equation. Okay, but Maxwell through his own, mathematical theoretical inconsistency with this law, what he did that to add such a term that can balance the both sides theoretically. This was the theoretical flaw in the Ampere's law, and the experimental flaw was that the for displacement of current, the displacement current was not described by Ampere's law. That means a capacitor between the two wires, and there is electric field or not between these two plates. So this cannot be described by Ampere's law. So for describing this scenario, Maxwell added this term, according to which there is an electric field in the um, plates, between the plates of this capacitor, and due to which there is a magnetic field circulated, given by the curl of magnetic field. Understood? So this was the relation given by Maxwell and Ampere for the curl of magnetic field. It is given by both current density, how dense currents are flowing, and the time derivative of electric field. It also matters. So this was the Maxwell's equations, Maxwell field equations, whole electrodynamics in a single video. Understood? If there is any doubt, so you can ask in my comment section, and we will reply your current comment and your problem. So now we have to revise what is given here. The mathematical requirements is that divergence of a vector equals divergence can be denoted by the del dot a, del vector dot a vector equals x partial derivative of uh, ax. Ax means the a of x component. Okay, a field of x component, a vector field, plus y partial derivative of a x component, a of y component. Okay, plus Z partial derivative of A of Z component. It is somewhat some tricky. Now, curl of A. What is the curl of A? How can we denote? By cross. Here is the by dot and here is by cross. Because this is somewhat the circulating means this is the vector, A vector, and the circulation. This is the A vector, and is the circulation is the curl of this A vector. This circulation. Okay, understood. So this circulation mathematically can be calculated by the determinant. Determinant of what? Determinant of this I cap, j cap, k cap, and in second row x partial derivative, y partial derivative, z partial derivative, third row a of x component, a of y component, a of z component. And to calculate this determinant, we have the expression here. Mathematically, we know. So this was the mathematical requirement to understand what we are going to deal with the Maxwell's equations. All these are here. You know, the mathematical requirements are here used. So now, if we understand the mathematical requirements, what are the physical meaning? The physical meaning of these mathematical requirements is also very useful, because without this we cannot apply in our daily life. So the physical meaning of divergence of A is the flux of A vector in a closed surface. The physical meaning of curl of A vector is the circulation of A vector around a closed loop. So this is the physical meaning of this divergence and curl of A vector. Understood? So this was the total electrodynamics in a single video. Thank you, everyone.